Hi, welcome to MACSGATE Academy. Let us continue the DBMS. In the last class, we have started normalization chapter, and there we have discussed functional dependencies and what are the uses of functional dependencies. So let us continue the uses of functional dependencies. So in this session, we mainly focus on how to find candidate keys using functional dependencies. So let us start it. What is a candidate key? One second, sir. I think there is some problem. Fine. So what is a candidate key? A candidate key is minimal set of attributes which can uniquely identify the records of a relation. So for this, we have seen so many examples. Suppose let us consider the example in which the relation is having attributes Aadhaar, name, age, PAN card, date of birth and address. Let us assume these are the attributes of my relation. What is the minimal set of attributes? First of all, the set of attributes. Suppose by using Aadhaar number, name, I can uniquely identify any person. So that means this is an example of a key, but it is not minimal. Why it is not minimal, sir? In this set, I have two attributes in which the first one is Aadhaar, the second one is name. If you observe very carefully, name is not mandatory. Name is not mandatory. That means even I don't have name in my collection, I can still find the records of the relation uniquely. So I need only Aadhaar number to identify any person uniquely. So this is a key as well as which is satisfying the property minimal attributes. Sir, we need to identify the person uniquely. That is the duty. But we need to identify it with minimum possible set of attributes. So this is an example of a candidate key. A relation may have so many candidate keys. Now the question is, in this example, we have knowledge about the attributes of the relation. That means we know what is Aadhaar number, what is name, age, PAN, date of birth. Now suppose I have a relation in which even I don't know the names of the relation. That means I don't know the meaning of the attributes. Then how to identify the candidate key? For that we use functional dependencies. So how to identify the candidate key? Whenever we know functional dependencies. As I told you, to find candidate key, we use the concept of attribute closure. We use the concept of attribute closure. What is attribute closure, sir? Suppose X is the attribute. Then the closure is denoted by X plus. Here what you write, sir? The collection of all attributes which can be derivable from X. The collection of all attributes which can be derivable or which we can identify. So which can be derivable from X. So this we have discussed how to find the attribute closure for a given set. Now we are going to use that concept of attribute closure to find the candidate keys. Then how to find it? Minimal set of attributes whose attribute closure contain all the attributes. So for the given set, we will find the attribute closure. If it contains all the attributes, then surely I can say it is a key, because the attribute closure contains all the attributes. That means we can derive all the attributes by using the given set. The second part is whether it is minimal or not. So these are the two things we need to identify, sir. The first one is whether the closure contains all the attributes or not. The next one is whether the given set is satisfying minimal property or not. So this is about finding candidate key. We will see some examples, sir. So before going to that one, what are the expected types of problems in our GATE exam? So the expected types of problems in candidate keys. The first one, they will give one particular set of attributes. So they will mention it, sir. Just we need to verify whether it is a candidate key or not, which is very easy. So just we need to identify whether it is minimal and whether its closure contains all attributes or not. Only two things. Instead of that one, sometimes they may ask, find all possible candidate keys or find the number of candidate keys. In this case, we need to consider each and every possibility for X and we need to verify whether it is a candidate key or not. So in the second case, X also we need to consider. Then how many possibilities are there for X? All those possibilities we need to consider. So these are the two types of expected problems on candidate keys. Fine. So let us start the first one. Whenever they given a set, we need to identify whether it is a candidate key or not. So whenever they given a set, we need to identify whether it is a candidate key or not. For that, the first step is I find the closure. I find the closure. If we got all attributes, if we got all attributes, then it means it is a key. Then the second one is whether it is minimal or not. Sir, suppose X contains only one attribute. X contains only one attribute. Surely it will be minimal because I cannot delete any attribute from X because I have only one attribute. Now suppose X is having two or more attributes. X is having two or more attributes. Let us suppose X is having two attributes, A comma B. Then if I want to say X is minimal, A should not be a candidate key. A should not be a candidate key. Why, sir? When A can do the job on its own, why we need B? That means B is not mandatory. When A can do the job on its own. Similarly, B should not be a candidate key because whenever P can done the job, whenever B can done the job, why we need A? So that we need to verify, sir. So let me explain more clearly with an example. Suppose I have a relation with four attributes A, B, C, D, and these are the functional dependencies. They has given four functional dependencies. Let us do the first expected type of problems. Whenever they given a set, we need to verify whether it is a candidate key or not. Please observe it. They given an attribute set with only one element. Since it is only one element, surely it will be minimal. Whenever the given attribute set is having only one attribute, surely it will be minimal. Clear, sir? Whenever it is having two or more, then I need to verify whether any subpart of it is a key or not. Now, what is the second step? The second step is what is the closure? With A, what are the attributes we can derive? With A, we can get A itself. Am I right, sir? Now, by using the functional dependency, A goes to B. From A, we can derive B. Then I have one more dependency, B goes to D. That means whenever we know the value of B, we can find D. Right, sir? Then we can use the next one. D goes to C. We already know the value of D. So just we are finding C. So what happens, sir? A closure contains all attributes. A closure contains all attributes. Sir, when the closure contains all attributes, we can say surely it is a key. Since we already know it is minimal and it is a key, I can say it is a candidate key. What is candidate key, sir? It should be a key with a minimal set of attributes. Am I clear in this? Let us do one more example. Verify D is a candidate key. I have only one attribute, sir. Surely it will be minimal. What is the second part? D closer. What is D closer? Let us do it. From the given dependencies. Sir, with the D, we can find obviously D. Then anything else? I think we can use third functional dependency D goes to C. With the D, I can find C. Yeah, fine. Then anything else, sir? No. I can get only two attributes. That means we are not getting all attributes. We are not getting all attributes. That means it is not a key. It is not a key. Sir, whenever it is not a key, surely it will not be a candidate key, because candidate key means first of all it needs to satisfy the property of key and then it should be minimal. Here it is not a key, so D will not be a candidate key. Is that clear? Now let us do one more example. Suppose I have a relation with 5 attributes A, B, C, D, E, and we need to verify whether A is a candidate key or not. Sir, whenever they given only one attribute, no need to verify minimal. So I think we got this point very clearly. Minimal. Fine. What is attribute closer, sir? The attribute closer from A I can get, from A we can get A. Then anything else? We have a functional dependency A implies B. Fine. Anything else, sir? Yes, we have a functional dependency B implies E. Fine. Then B implies A. We already have A. Then anything, sir? With the E, I can get C. With the E, you can get C. Then I want D. Can we get D, sir? No, not possible. So we don't have all attributes. D is missing. D is missing. So it is not a candidate key. Of course, first of all, it is not a key and hence it is not a candidate key. Let us do one more. Suppose I want to verify whether D is a candidate key or not. It is having only one attribute. So surely it will be minimal. Then the closure of D. What is closure of D in this case? With the D we can get D. Anything else, sir? With the D I can get C. Then I think we don't have. We have only 2. So we didn't get all attributes. Not getting all attributes. Hence, it cannot be a key and hence it cannot be a candidate key. So it is not a candidate key. Am I clear in this? Suppose I want to find whether AD is a candidate key or not. Now please look at this, sir. I have 2 attributes. Whenever I have 2 attributes, first I need to verify whether any attribute on its own is a candidate key or not. Suppose in this example, I got A is a candidate key. Then don't verify anything. It will not be a candidate key because it is not minimal. Now in this example, I already verified A is not a candidate key. Even D is also not a candidate key. Since both were failed on their own, sir, both were failed on their own. This is not a candidate key. This is not a candidate key. So AD is surely minimal. AD is surely minimal. Then what is the closure of AD plus? With A comma D, I can get AD. Anything else? With A, you can get B. Yes. With B, you can get E. Yes. Then with E, I can get C. You got all attributes, sir. So you got all attributes. So it is a key. It is minimal as well as key. So it will be a candidate key. Hope you understood the process. So when the given set contains one attribute, when the given set contains one attribute, then simply verify whether it is a key or not. Suppose I have two attributes. Yeah, I think here no to write yes, right? Yes. So whenever you have two attributes, suppose they are x comma y. First of all, it should not be a candidate key. It should not be a candidate key. Whenever x is a candidate key, the combination of x comma y cannot be minimal. So first we need to make sure that individually they are not candidate keys. Then only we start finding the closure. If we got all attributes, it will be a candidate key. Suppose we are not getting all attributes for this x comma y. That means they are not sufficient to identify the record uniquely. So it will not be a candidate key. Hope you understood it. So the second type of expected problem is finding all candidate keys for the relation. Finding all candidate keys for the relation. For that, what we need to do, or what is the general process? Okay. First of all, since I have four attributes, I verify sets with one attributes are candidate keys or not. Suppose I got this is a candidate key and this is a candidate key. These two are not candidate keys. So that means in the next stage I will consider sets with two attributes. Now I don't consider this A comma B. Why don't consider, sir? Because A already a candidate key. So this cannot be minimal. This cannot be minimal. So I should not consider any combination with A. So this is not candidate key. Even this is also not candidate key. Hope you understood it. So we need to write only the combinations in which the individuals are not candidate keys. In this case, let us consider B comma D. Please verify it. B is not a candidate key. D is not a candidate key. So this we can verify. Like that, whenever the previous level, that is, if the set with one attributes are candidate keys, we don't consider those attributes in next level. Right? So let me explain that with this example. In this case, we have one more point to discuss, sir. That point we discuss in next example. So this is the first point. How to start, or what are the possibilities we need to consider. Here I have totally four attributes. So let us start with first one. A closure. What is A closure, sir? With A, I can get A. Anything else? Sir, please observe it. A is giving B. A is giving C. Then, yeah, I have this one. B, C. This is giving D. So that means this is a candidate key. Let us verify the remaining also. What is the second possibility I need to verify? B. With B, I will get B. Anything else? Only with B, I cannot get anything, sir. So that means it cannot be a candidate key. This cannot be a candidate key. So let us go to the third option. C. With C, I can get C. Anything else? No, sir. So C on its own cannot be a candidate key. What about the next attribute, sir? The next attribute is D. So what is D closer? D is fine. Then with the D, I can get A. Fine. Then with the A, you can get B. With the A, you can get C. So this is also a candidate key. So we have completed one attribute sets. Now we need to consider two attribute sets, then three attribute sets, then four attribute sets. But while we are listing two attribute sets, we don't consider the attributes which are already candidate keys. So in next stage, we don't consider A comma D. Suppose I can consider all these possibilities, sir. AB, AC, AD, BC, BD, CD. These are the possible attribute sets with two attributes, but they cannot be minimal, sir, because the first one contains A. So this cannot be minimal. This also contains A. This cannot be minimal. This also contains A. It cannot be minimal. What about here, sir? B comma C. I think only we have A comma D. So this we may consider, sir. This one I should not consider. D is there. This one D I should not. So I need to consider only BC. What is the closure of BC, sir? B comma C I can get. Anything else? Yes, of course. With BC I can get D. Then with D I can get A. So we got all attributes. So B is not a candidate key, C is not a candidate key, but if we combine them, it is becoming a key. So this is an example of a candidate key. In next stage, I need to consider three element sets. I need to consider three element sets. What are the possible three element sets with ABC, sir? Sorry, A, B, C, D. A, B, C, A, B, D, A, C, D, D, C, D. Actually, no need to consider all these, sir. A, already a candidate key. So leave it. A, leave it. A, leave it. Then BC. BC is already a candidate key. So D may be extra attribute. I don't need it. So we don't have any candidate keys with three elements. When I don't have any candidate keys with three elements, then no need to verify the next one because we already completed all the attributes in the previous level. Hope you understood it. So in this case, I explained the procedure. What are the possibilities we need to consider? First, we need to consider one element sets. Then you need to consider two element sets. Then you need to consider three element sets. While you are considering three element sets, don't consider the attributes which are already candidate keys. That's it. Even if you can consider, no issue, sir, but the problem becomes lengthy. That's it. Hope you understood it. So now let me give the second point, which is very important, with one more example. Suppose I have a relation with 5 attributes A, B, C, D. Now the thing is, first of all, find the attributes. Find the attributes which are not present on the right side of any functional dependency. So the first step is find attributes which are not on RHS of any functional dependency. Suppose I have a attribute to X. It is not present on right side of any functional dependency. What does that mean, sir? I cannot get the value of X by using anything else. I cannot get the value of X by using anything else. Then in such scenario, what I need to do? In my candidate key, X must be present. Because if X is not there, who will get the value of X, sir? No one can get it because X is not present on right side of any attribute. In this example, A is present here. It's fine. B is present here. C, it is present in E goes to C, sir. What about D? Sir, please observe it. D is not present on right side of any attribute. What about E? It is present. That means let me give two conclusions. The first one, D is not present on RHS of FDs. So what does it mean? I cannot get the value of D by using anyone else. So D must be a part of candidate key. D must be a part of candidate key. That means no need to consider the single sets A, B, C, D, E. In this example, these are the possibilities, sir. Here, this no need to consider because D is not a part of it. This no need to consider. D is not a part. D is not a part. Here, D is a part of itself, right? So this also I should not consider. Now what I need to do is in singleton sets I need to verify only this one. D closure. By luckily, if the closure contains all attributes, it will be the one and only candidate key. It will be the one and only candidate key. Why? Because D must be a part of candidate key. Whenever this is a candidate key, whenever this is a candidate key, there will be no other candidate key, sir. Why? Because suppose I written D, then since D on its own itself is a hero, this cannot be a minimal set. Suppose if I don't include D, since D is not present, according to second point, we cannot get all attributes. Is that clear, sir? If D is present, it cannot be minimal. If D is not present, we don't get all attributes. All this is only when D itself is a candidate key. So in this example, let me verify. What is D closure, sir? With D, I can get D. Anything else? Yeah, we have a dependency. D goes to A. So D comma A. Then with A, I can get B. Then with B, you can get E. Then with E, you can get C. We got all attributes. So it is a candidate key. Since it is a candidate key, there will be no other candidate keys. Hope you understood it. So first we need to identify the attributes which are not the right side of any functional dependency. Whenever they are not on the right side, they cannot be derived from anyone else. So it must be a part of candidate key, right? Let us do one more example. Let us consider this relation. First A is present here. B is present here. C, it is present here. D, it is not present. E, it is present. So again, D is not a part of, sorry, D is not on RHS of any FB. So what is your conclusion, sir? D must be a part of candidate key. D must be a part of candidate key. So what does it mean, sir? No need to consider the sets which don't contain D. So that's why we don't consider A. We don't consider B. We don't consider C. We don't consider E. But you can consider D because D is part of it. Now the third step. What is D closer? What is D closer? In this case, what is D closer, sir? With the D, I can get D. Anything else? With the D, you can get C. Then with the C, I don't get anything. So we are not getting all attributes, sir. We are not getting all attributes. That means D on its own cannot derive all the attributes. So in this case, we try now two sets because one sets we already completed. With the two sets A comma B, can I consider this, sir? No. D must be part of it. So I should not consider AB. So let us consider, let us write like this. It will be comfortable for us. DA, DB, DC, DE. These are the possibilities I need to verify. Let us verify the first one. DA. With the D comma A, what we can get, sir? D, A. I have D goes to C. I can get C. Anything else? S. With A, I can get B. With the B, I can get C. So we got all attributes. So this will be a candidate key, right? Let us start the second one. DB closer. What is DB closer? DB. Anything else? With the D, you can get C, S. Then with the B, you can get E. With the B, you can get E. With the B, you can get A. So that means the second one is also a candidate key. Hope you understood it. Now let us try the third one. DC. What is closer of it? D comma C. Anything else? I think no, sir. So this cannot be a candidate key. Then what about the third one? DE. With the D comma E, I think we can get a D, E. Then with the E, I can get C. Anything else? No. So we cannot get all attributes. So this is not a candidate key. Then try 3 attribute sets. In that also D must be there. Then 2 more entries. D, A, B. Can we try this, sir? No. Please check it. D, A. It's a part of it. I don't try it. Can I consider D, A, C? No. Because DA is part of it. It is already a candidate key. Then any other possibility? D, A, E. This also I should not consider. Fine. Anything else you can write? D, B, C. Can you do it, sir? With the DB, it is already candidate key. Don't try it. D, B, E. DB is already a candidate key. I don't try it. Then any other possibility? D, C, E. Sir, please verify. D is not a candidate key. DC is not a candidate key. EC is not a candidate key. Even DE also not a candidate key. So I need to try this. DCE plus. What is the closure of it? DCE. Anything else you can get, sir? DCE. That's it, right? So still it is not a candidate key because we are not getting any other attributes. Now we need to try with the 4 attribute sets. But when you try with the 4 attribute sets, 1 minute, sir. When you try with 4 attribute sets, D, C, E, okay. If I include A, the combination of these two is a candidate key. So don't try it. D, C, E, B. The combination of these two is a candidate key. So don't try it. So we don't go for 4 attribute sets. In this example, how many candidate keys you are having? You are having 2 candidate keys. Hope you understood the process. Let us do one more example. Sir, A is present here. B is present here. C is present here. D, no sir. E, no. F, yes. So D comma E is not present. DE is not present on RHS of any functional dependency. So what does it mean? D comma E must be a part of candidate key. DE is must be part of candidate key. So let's try directly D. What is the closure of D comma E? D, E. Anything else? With the D, I can get A. S. Then with the E, you can get F. Then with F, you can get B. With B, you can get C. So we got all values. What does it mean, sir? It is a candidate key. Whenever it is a candidate key, now the question is, does we need to consider 3 element attributes? Does we need to consider, sir? No, because if I don't consider these 2 in my collection, I don't get those 2 attributes because they are not part of any functional dependency, right? Suppose if I include, it is already a candidate key, so it cannot be a minimal key. For example, if I try this DEA, since it is a candidate key, it cannot be minimal. Suppose I don't include DE. Suppose I have considered only ABC. Can you try it, sir? No, because even if you try, you will not get all attributes. With ABC, what you get, sir? A, B, C. Anything else? No. So we are not getting all attributes. Hope you understood it. So this is the story about finding the number of all possible candidate keys. Is that clear? Let us do one of the previous question. Just go through the question, sir. Let R equal to a 6 element relation A, B, C, D, E, F. It's a relation schema with the functional dependencies. C goes to F, E goes to A, EC goes to D, A goes to B. Totally 4 functional dependencies. They are the 4 functional dependencies. Which of the following is a key? When they ask which of the following is a key, don't take any risks, sir. Simply let us try each and every option. Sir, if you want, you can follow the procedure which is not on the right side of anything like that. Instead of that one, let us try the simplest trial and error method. What is CD closer? What is CD closer, sir? So with C, D, I can get D. Then with C, I can get F. Why so? C implies F. Then anything else? No, sir. So it is not a key. Sir, it is not a candidate key. Sir, it is not a key. And hence it is not a candidate key. Suppose let us try the second option. What is the second option, sir? EC. What is the closer of EC? EC. Anything else? With the E, I can get A. Fine. With EC, you can get D. Then with the C, you can get F. What about B? With A, you can get B. Sir, please observe it. We got all attributes. So it is a key. It is a key. Whenever it is a key, the second step we need to verify is whether it is minimal or not. Suppose here in the option they given only one attribute. Surely it will be minimal. But here they given two attributes. So what I need to do, sir? I need to consider those two attributes separately. Whether you are able to get the job or you are able to do the job by E itself. What is the closure of E in this example? E, then A, then B. That's it. So this is not a key. So it cannot be a candidate key. What about the second one? What is the second one, sir? C, right? Yeah. So what is the closure of C? C, fine. C implies F. Then I got only two. So it is not a candidate key. Since the attributes individually not a candidate keys, it is minimal. So it is an example of a candidate key. Hope you understood it. Like that, whenever they ask to verify the given one is a candidate key, directly verify by considering the option. Right? Suppose, let us consider the next problem. Consider the relation with attributes E, F, G, H, I, J, K, L, M, N and the set of functional dependencies like this. Then they given set with one attribute, two attributes, three attributes, five attributes. Let us try the options with minimum number of attributes. Fine. So let us try it. Sir, what is option A? E. What is the closure of E, sir? With E, I think I will get only E. Any possibility? No, sir. So I am able to get only one. Not a key, hence not a candidate key. Let me write directly. What about the second option? The second option E, F. With E, F, I can get E, F. Then with E, F, I can get Z. Please check it, sir. EF implies G. Then With F, we can get I comma J. I comma J. Fine. Then anything else? No, sir. So this is not a candidate key. Right, sir? So let us try the third one. Option C. E, F, H. What is the closure of it? E, F, H. Any other possibilities? Yes. E, F implies G. F implies IJ. Then EH implies KL. Then K implies M. L implies N. We got all attributes. So it is a key, sir. Now the story is whether the individual ones are keys or not. Sir, only E, only F, only H, only EF, only EH, only FH. Try for this. E already we verified, sir. This cannot be. F, with AF we are unable to get anything. So this is not. EF we tried. What about H, sir? With H, what you can get? No, sir, I can get only H only. So this cannot be. EH, E comma H I can get. Anything? K comma L, M comma N. Then what about G? Not getting. What about FH? F, H, I, J. That's it. So not. So it is key plus minimal. Hence it is a candidate. Sir, if you don't want to verify like this, so just follow the process what we have done in the second case. Now let us consider this. Let us do this question by using the second procedure. Okay. What are the functional dependencies? These are the functional dependencies. A is present here. B is present here. C is present here. D is present here. What about EH? No. So EH not present on RHS of FDs. EH is not present on RHS of FDs, right? So EH must be part of candidate keys. EH must be part of candidate keys. Am I right, sir? Please verify the options. Here H is not there. Here also H is not there. Here H is there. So I need to try, sir. I don't know whether it is. H is there. EH, yes. EH, it's not there. Since it is not correct, this cannot be correct. Here AEH, BEH, DEH. Of course, since three options were eliminated, the last one will be our answer. If you want, you can verify it. AEH. What is the closure of this? AEH. Then with A, I can get B. Then with E, I can get C. Then with BC, you can get D. We got everything, sir. Like this, you can verify the remaining BEH closure. DEH closure. Surely they will find all the attributes because that is the one and only option we are having in this question. I think you can do it on your own. Can I leave it, sir? Yes. So let's go for the next one. Just go through the question, sir. Relation are having 8 attributes: A, B, C, D, E, F, G, H. Fine. Then fields of R contain only atomic values, and F equal to, they given some functional dependencies. CH implies G, A implies BC, B implies CFH, E implies A, F implies EG. The set of functional dependencies. So that F plus E is exactly the set of FDs that hold for the relation. Now the question is, how many candidate keys does the relation has? So since they ask about how many candidate keys, I don't have any other choice. Consider 1 attribute sets, 2 attribute sets, 3 attribute sets. Like that I need to continue. But before going to that one, please verify, are there any attributes which are not on right side of any functional dependency? If there are some such attributes, it can reduce our work. That's it. Even if you don't verify, you can continue, sir. But if you can identify the attributes which are not present on the right side of any functional dependency, it will reduce our work. That's it. So A is present here. What about B? It is present here. C, it is present there. What about D? D is not present, sir. What about E? ES. What about F? S. What about Z? S. What about H? S. So D is not present. So D must be a part of candidate key. So first try directly D closure. What is D closure, sir? With D I can get D. Anything else? Please check it. No, it cannot get anything. So this cannot be a candidate key. D on its own cannot be a candidate key. Sir, suppose it is a candidate key, our work was done. I have only one candidate key. So now I need to try 2 element sets. Let us try one by one. What are the possible 2 element sets, sir? D must present AD, BD, CD, DD, it's not needed, sir, right? So ED, FD, ZD, HD. So we need to find all these. Can we do directly here? With the AD, I can get AD. Anything else? With the A, I can get BC. Then with the B, I can get C, F, H. Okay, A, B, C, D, E, F. What about Z? With the F, we can get EG. So we got all attributes. It's a candidate key. What about BD? B, D. Anything else, sir? With the B, D, S. With the B, I can get C, F, H. C, F, H. Then with the F, I can get E, G. What about A, S? With E, we can get A. I think I got all attributes. Fine. It is also a candidate key. What about CD? With the C, D, I can get only CD. Anything else? No, sir. So this cannot be a candidate key because we are not getting all attributes. What about fourth one? E, D. Anything else? With E, I can get A. Fine. Then With A, I can get BC. With B, I can get C, F, H. A, B, C, D, E, F, G I want. With F, I can get G, H. Yes, we got. This is one more. So by this time, this is one candidate key, this is second candidate key, this is third candidate key. What about FD? FD. With F, you can get EG. Then with E, you can get A. S. With A, you can get BC. Then with B, you can get F comma H. I think F already there, sir. So let's write only H. We got all attributes. I think F, D, E, G, A, B, C, H. What about GD? GD is for sure. Anything else? With GD, we don't get anything, sir. So this cannot be a candidate key. What about HD? With HD, I can get only HD. So this is also not a candidate key. Now I need to try 3 element sets. I need to try 3 element sets. Sir, when you try 3 element sets, don't consider which are already candidate keys. So what else you can consider, sir? CD, GD, HD. These are the only possibilities. With this, what you can form? C, G, D. C, G, H. Then anything else, sir? G, D, H. Am I right? So what about C, G, D? C, G, D. Then with the C, G, D, anything else possible, sir? No. So this cannot be a candidate key. What about the second option? C, G, H. C, G, H. With C, H, I can get G. G already I have. Then with the C, G, H, nothing is possible. So the second one is also not a candidate key. What about the third one, sir? G, D, H. G, B, H. Nothing is possible, sir. So this is also not a candidate key. What are you supposed to do, sir? I need to consider 4 element sets. I need to consider 4 element sets. To consider 4 element sets, I need to consider the variables only from this part. Because if I consider anything else, it cannot be minimal. So with this, I can form only C, D, G, H. What is the clause of this? With C, G, D, H, what you can get? C, D, G, H. They are for sure. Then with CH, I can get G. G already there. Then nothing is possible, sir. So this is also not a candidate. Hope I understood it. Now 5 element sets. Can you write any 5 element set with 4 variables? Not possible. So five element sets, not possible. So hence 6, 7, 8 also not possible because I have only 4 variables. So how many candidate keys you are having, sir? 1, 2, 3, 4. Anyway, let me write it here. The candidate keys AD, BD, ED, FD. So these are the 4 candidate keys that the given relation is having. Hope you understood it. Is that clear, sir? Yes. So this is about finding candidate keys by using functional dependencies. Hope you understood it. Candidate keys play a very important role in normalization. So we should know how to find the candidate keys by using the given relation and functional dependencies. So that is for today's session. Thank you.